Why is damped natural frequency important for engineers? Imagine trying to swing a pendulum. If you push it gently, it swings back and forth smoothly. But if you push it too hard or if there's resistance, the swing slows down and stops sooner. That resistance is what damping is all about. Now, think about how engineers need to understand how systems vibrate when damping is present. This is where the damped natural frequency comes into play. It's a key number that tells us how a real-world vibrating system will behave when energy is lost over time. Every mechanical system that can vibrate has a natural frequency. That's the rate at which it would oscillate if there were no energy losses. But in real life, damping mechanisms like friction, air resistance, or material resistance are always there. They cause the vibrations to slow down and eventually stop. Because of this, the actual frequency at which the system vibrates when damping is present is called the damped natural frequency. It is slightly lower than the undamped natural frequency. Knowing the damped natural frequency is important for predicting how a system will respond to external forces or disturbances. If you know this frequency, you can design systems to avoid dangerous resonance conditions. Resonance happens when an external force matches the system's natural frequency, causing large vibrations that can lead to damage or failure. Damping shifts the oscillation frequency, helping engineers steer clear of these risky situations. This frequency also helps in designing vibration control devices like shock absorbers in cars or vibration isolators in buildings. These devices are tuned to the damped natural frequency to reduce harmful vibrations and improve safety and comfort. It also plays a role in energy dissipation. The rate at which vibrations decay depends on the damping. The damped natural frequency tells us how quickly the vibrations fade away, which is vital for understanding how energy is lost in the system. Engineers use this concept across many fields. For example, in automotive engineering, it helps design suspension systems that absorb shocks smoothly. In civil engineering, it guides the creation of buildings that can withstand earthquakes by controlling vibrations. Even in electronics, it helps in designing circuits that avoid unwanted oscillations. Mathematically, the damped natural frequency is calculated by taking the undamped natural frequency and multiplying it by the square root of 1 minus the damping ratio squared. The damping ratio is a measure of how much damping is present compared to the critical amount needed to prevent oscillations from growing. This calculation helps engineers determine the actual oscillation rate when damping is involved. In practical terms, knowing the damped natural frequency allows engineers to analyze how quickly vibrations die out, design components to control or withstand oscillations, and ensure systems operate safely without excessive noise or wear. It's a fundamental part of designing reliable, efficient, and safe mechanical systems in the real world. Understanding this frequency helps engineers create systems that perform well under real operating conditions, where damping is always present.